All right, thank you, Jean-Pierre. For the audience who may not know, in fact, I've worked with Jean-Pierre for 33 years almost now.
Yeah, it's a long time ago.
I started my career working on Huygens as a young graduate trainee, actually at ESTEC, and Jean-Pierre was the project scientist. Um, I'm sorry not to be with you today. I'm actually in Chicago at a planetary acoustics conference, and I'm actually giving a talk later today about ingenuity. So it was good to have the update from Teddy just on where the hell he is today. Um, so Dragonfly is NASA's fourth New Frontiers mission, and is going to Saturn's moon Titan, which was, of course, the destination of the Huygens probe. So Jean-Pierre knows it very well. So Dragonfly is a scientific mission. It is conceived to address scientific questions, and those really relate to the features that make Titan such an interesting place, namely the rich organic chemistry that has a bearing on the origins of life. I mean, we don't necessarily think that Titan has life today, but the chemical processes on Titan can likely tell us a lot about the chemical processes on the early Earth that led to the progressive complexity of organic processes that eventually led to the execution of the functions of life. Right? At some point, we went from simple chemical systems to those that can yield free energy, metabolism, and those that can store information and replicate information. And those chemical steps are frozen on Titan's surface, waiting for us to unravel. And so Titan is an outstanding location for studying astrobiology, and it's a unique environment in terms of being able to access the chemistry. We want to understand the materials on Titan's surface, and those were always going to be the big question after Cassini and Huygens. Cassini and Huygens were not equipped to analyze Titan's surface chemistry. So mobility is really key in this exploration, in that it allows us, just as the rovers do on Mars, it allows us to access particular environments, and the particular aspect that we want to explore on Titan is where liquid water may have interacted with the abundant organics on Titan. We know there are, for example, sand dunes on Titan that are made of dark material that is organic rich. But there is also a handful of impact craters where there has been a lot of energy deposited in the crust, where the crust, which is, we think, water ice, has melted to form liquid water. And that liquid water interacting with the organics leads to a much wider range of compounds, including things like pyrimidines, the bases that encode information in DNA, or amino acids, the building blocks of life. So there's rich organic chemistry on the surface, we believe, and we believe we know the general location of these. But of course, we'll get so much better information, much higher resolution imaging, and a much better perspective from a platform in situ. We can take aerial images just like the reconnaissance images that Teddy showed from Ingenuity. The difference is the rover and the aircraft are the same vehicle. So what we want to do is basically roam around, take aerial images, measure surface composition at fixed locations with a sampling system, and we want the sort of ancillary data to help organize that voyage of exploration. So we passed our preliminary design review earlier this year. So the technical baseline for the mission is well established, and we're working presently towards a June 2027 launch, with arrival in 2034. That's basically one Titan year after Huygens, and that's useful in that it lets us use the Huygens in situ information as ground truth, right? We know what the winds are going to be like because we're going to the similar latitude in the same season on Titan. Our plan is to conduct a little over 3 years of exploration, traversing several tens of kilometers. I mean, the landing ellipse shown in the upper right is about 70 kilometers across in the narrower dimension. The Selk impact crater is about 80 kilometers across. So we'll land safely among the sand dunes where we know the terrain will be relatively free of rock and gully hazards. And then we'll have a lot more information on which to plan a progressive sort of migration towards the crater where we think these interesting rock deposits are. We're doing lots of technical work, of course, right now, including rotor testing in some of NASA's advanced facilities like the Transonic Dynamics Tunnel at Langley Research Center. One of the great things about a rotorcraft on Titan is that you can do terrestrial field tests, right? I mean, the sky crane that delivered the Perseverance and Curiosity rovers, never flew on Earth, right? All the preparation had to be grounded in computer simulations. But we can actually build in fact, it's a 0.56 scale, it's not quite half scale, vehicle and fly it around in deserts on the Earth to rehearse the operation of the vision navigation system and the autopilot algorithms. And we use some dunes actually in Southern California for that. We are just commissioning, I think next week, a new Titan chamber at APL that's big enough to put the whole lander inside. Just for your reference, the door on that chamber, which goes down to 90 Kelvin, that's a 16-ton door, and I hate to think how much liquid nitrogen it's going to use to cool it down each time we do a test. But we're plowing ahead with the development, and as I say, working towards launch in a few years. Unlike Mars, which is only eight months away, outer solar system exploration is unfortunately not a business that lends itself to instant gratification. But I've been there, done that, right? When I was a young engineer, 22 years old at ESTEC, Cassini's launch in 1997 seemed a long way away, and the 7-year trip time that Cassini and Huygens underwent to Titan seemed like forever, but it comes sooner than you think. So Titan as an environment is very conducive to flight because it's a moon. It's got a gravity similar to the Earth's moon, and its atmosphere is 4 times denser than ours. And those two factors make it very, very easy to fly. Flying is very straightforward. There's nothing like the challenge that Ingenuity had on Mars. If you do the quick calculations, you find it takes about 40 times less power for a given vehicle to hover on Titan than it does on Earth. And actually, I recognized this back in 2000, and this artist impression, which actually looks a little bit like Ingenuity for similar reasons, and actually it's taking a picture of the Huygens EDL hardware in this impression. It is such an obvious and appealing way to explore Titan, but in 2000 it seemed like science fiction. In the interim, of course, we've had the development of the MMRTG, the radioisotope power supply that Curiosity and Perseverance used, and we've had the drone revolution, right? The sensors, the autopilots, the electronic speed controllers, the better batteries, the better motor magnets. These have all been relatively incremental technology developments, but together they make something like Dragonfly possible. So Dragonfly, of course, is not just a rotorcraft, it's the whole mission. We have launched, we spent 7 years in space going out to Saturn. We have an entry, descent, and landing. Much like Perseverance or Huygens. Unlike Ingenuity, which was deposited on the ground by the Perseverance rover, we land under our own power. We separate from the back shell during EDL, and then we operate as a self-contained mobile lander. 99% of the time, we're just sitting there. like a regular planetary lander, but of course we fly to new places in between. The configuration of the vehicle, an octocopter, really is dictated by maximizing the rotor area. That's what minimizes the power you need to fly. But of course, we have to fit inside the aeroshell, and the most efficient packaging leads to a sort of 4-rotor set configuration. We actually have two rotors in each corner, so we're really an octocopter that allows us to tolerate the loss of a rotor or motor should something fail. The vehicle actually has rotor blades that are quite similar to the size of those on Ingenuity, 1.4 meters in diameter. The principal investigator of the mission, Zibi Turtle at APL, is shown there for scale with one of the rotor blades. We have to send all the data back from Dragonfly direct to Earth. So we have a dish antenna that folds flat on the back of the lander for flight. That's a key aspect of the mission. And Titan is very cold. The environment is 94 Kelvin and the atmosphere is thick, so it's very, very chilling. So we rely on the quote unquote waste heat from the RTG. It puts out about 100 watts of electrical power, but also 2 kilowatts of heat. And we have to take very special measures to conserve that heat inside the body of the vehicle. We have, like the Huygens probe, about 5 or 7 centimeters thick foam insulation to stay warm. The operations concept is a little bit like Ingenuity's in a way. We basically charge up a battery continuously with the 100 watts from the RTG. And we use it very quickly when we fly. It takes about 10 kilowatts to fly. But during the Titan night, which is 8 Earth days long, we have really nothing else to do except charge that battery up, because we're in darkness and we're on the side of Titan that is facing away from the Earth, so no communication is possible. Then during the Titan day, in the morning, calm morning, we'll typically execute a flight that's 20 minutes or 30 minutes long, and that burns up about half of the battery energy. We use the rest of the energy at intervals during the rest of the Titan day, typically once an Earth day, make a downlink of science data, and we have ground in the loop operations to decide whether to take samples or which cameras to use and so on. Next, because I know we're running out of time. Yeah, this is the crater. We know from analog environments on the Earth that these sand dunes, which are about 3 kilometers apart, have interdune areas that are very flat, very accommodating for landing. And once we get off the dune terrain, we'll move towards progressively rougher terrain, but more scientifically interesting terrain near the crater. But we'll be able to do that with the aerial imaging from previous landings. In fact, our operations concept, after the very first landing, we can make very high resolution surveys with a LiDAR that can detect individual rocks and gullies to scout out new locations. So after that first landing, we never need to go anywhere that we haven't assured ourselves is perfectly safe. But of course, the flying is only half an hour every couple of Titan days. So basically once a month. The flight distance will be several kilometers. We're going to be able to leapfrog over the dunes, basically. So just as an aside, aerodynamically, an octocopter is really quite a complicated vehicle. When you're in forward powered flight, the rear rotors are in the downwash of the upper forward rotors. So we do a lot of computational fluid dynamics simulations to understand the operating environment of the envelope of the vehicle. And as I mentioned earlier, we're anchoring those simulations with wind tunnel data and with terrestrial free flight data. We have a sophisticated science payload to the end. A set of cameras looking downwards, sideways, forwards. We also have a microscopic imager that looks at the ground right under the lander at the sand grain scale. The illumination on Titan is faint, about the same, about 1,000 times full moonlight on the Earth, but that's, as Huygens showed, plenty to take images with. But during the night, actually, we'll take some images with artificial illumination. We have an LED array that forces sort of artificial color. And there's ultraviolet illumination in there too. A lot of organic compounds like quinine, for example, fluoresce in the ultraviolet, so we'll look at that. We have a gamma ray spectrometer to measure the elemental composition in a non-contact way. Are we sitting on an ice sheet, or is it organic rich? And then if we choose to take samples, we analyze those with a very sophisticated mass spectrometer that can tease apart the organic chemistry. We have a weather package and, in fact, a seismometer that lets us interrogate the internal structure of Titan. We'll learn how deep its ice crust is when we think there's a water ocean beneath. So if you want to learn more, we have a lot of resources at our website, dragonfly.jsuapl.edu. And if you're interested in learning more about Dragonfly and in particular the sort of comparing and contrasting with Ingenuity, I have a book recently published by the AIAA. So thanks for your attention. Sorry not to be with you in person.